Which set below form a basis for R3? There may be more than one answer. A set of vectors S in a vector space V is a basis for V if, number one, the set S is independent, and number two, the set S spans V. In our case, because we have a set of three vectors in R3, if the set of vectors form a basis for R3, then there exist three scalars, C sub 1 through C sub 3, such that the linear combinations of the three vectors is equal to any vector x in R3. And since we have three vectors in R3, we have two options to test to see if the set is a basis for R3. Number one, we can check to see if the set of vectors is independent. Remember, the test for independence is to solve the homogeneous vector equation shown here below, and if the solution is only the trivial solution, the set is independent. If there is more than the trivial solution, the set is dependent. Because we have a set of three vectors in R3, if the set of vectors is independent, the set also spans R3 and is a basis for R3. The second option is to check to see if the set of vectors spans R3. If it does, again, because we have a set of three vectors in R3, the set is also independent and is a basis for R3. We will take a look at both approaches. Let's begin by considering the first set of vectors, and let's perform the independence test. So we form the linear combinations of the three given vectors and set it equal to the zero vector, which I've done here in the upper right-hand corner. From here we can write the augmented matrix, where the first row is -1, 3, 8, 0, the second row is 0, 1, 3, 0, and the third row is -1, 6, 17, 0. For the next step, we write the augmented matrix in reduced row echelon form, which I've done here on the right. And let's go ahead and label the columns C sub 1 through C sub 3. Notice how we have three rows with a last row of zeros, which means we have a dependent system, and therefore the set of vectors is dependent, not independent. But for more detail, notice how the first row indicates that C sub 1 plus C sub 3 equals 0. The second row indicates that C sub 2 plus 3 C sub 3 equals 0. And for the third row, we have a row of zeros. If we identify the pivot positions, which are row 1, column 1, and row 2, column 2, we can see the pivot columns are column 1 and column 2, and therefore C sub 1 and C sub 2 are the basic variables, and C sub 3 is a free variable, which we can indicate as C sub 3 equals C sub 3. So because we have a dependent system, we have more than the trivial solution, and therefore the set is dependent, not independent, and therefore does not form a basis for R3. The other option would be to perform the spanning test, where we take the linear combinations of the three given vectors and set it equal to any vector in R3, which I've done here, where the components of any vector in R3 are x1, x2, and x3. And then we form the augmented matrix, which is the same as the augmented matrix as above, except column 4 is now x1, x2, and x3, rather than the zero vector. Performing row operations to write the augmented matrix in reduced row echelon form, we have the matrix here on the right. Notice on the fourth column we have x prime 1, x prime 2, x prime 3. These would be some constants after performing the row operations to write the augmented matrix in reduced row echelon form. So notice here, if we focus on the third row, we have 0 equals x prime sub 3. Well, this is going to be false whenever the vector x in R3 does not have a third component equal to 0, which we would then have a contradiction indicating there are not values C sub 1, C sub 2, and C sub 3, where the three vectors can be written as a linear combination to form any vector in R3. This means the set does not span R3, and therefore does not form a basis for R3. So going back to the original problem, we do not check the first set of vectors, and we move on to the second set of vectors. And again, we'll show both tests. For the independence test, we have linear combinations of the given three vectors equals the zero vector. The next step is to form the augmented matrix, and then write the augmented matrix in reduced row echelon form. Again, labeling the columns C sub 1 through C sub 3. The first row indicates that C sub 1 equals 0. The second row indicates that C sub 2 equals 0. The third row indicates that C sub 3 equals 0. We only have the trivial solution, which indicates the set of vectors is independent. Because we have 3 vectors in R3, this also means the set of vectors does span R3, and therefore the set forms a basis for R3. Similarly, for the spanning test, again, the only difference is we set the linear combinations equal to any vector in R3 with components x1, x2, and x3, form the augmented matrix, and then write the augmented matrix in reduced-row echelon form. Again, where x prime 1, x prime 2, and x prime 3 would be the constants formed by performing the row operations to write the augmented matrix in reduced-row echelon form. The first row indicates that C sub 1 is equal to x prime 1. The second row indicates that C sub 2 equals x prime 2. And the third row indicates that C sub 3 equals x prime 3. This tells us that any vector in R3 can be written as a linear combination of the given 3 vectors. The set spans R3, and because we have 3 vectors in R3, the 3 vectors would also be independent. The set of vectors does form a basis for R3. So we go ahead and put a check next to the second set, which does form a basis for R3, and then we check the final set of vectors. Again, showing both tests. For the independence test, we have our linear combinations equal to the 0 vector. We have the augmented matrix, and then the augmented matrix in reduced-row echelon form. So just like the second set, we know that C sub 1 must equal 0, C sub 2 must equal 0, and C sub 3 must equal 0, indicating the set of vectors is independent, and because we have 3 vectors in R3, will also span R3, the set of vectors does form a basis for R3. And then for the spanning test, again, the only difference is we set the linear combinations equal to any vector in R3 indicated by x1, x2, x3, write the augmented matrix, and then write the augmented matrix in reduced-row echelon form. For the first row, we have C sub 1 equals x prime 1. The second row indicates C sub 2 equals x prime sub 2. The third row indicates that C sub 3 is equal to x prime 3. So there are values, C sub 1, C sub 2, C sub 3, where any vector in R3 can be written as a linear combination of the given set of vectors. So the set does span R3. Because we have 3 vectors in R3, they must also be independent. Once again, verifying the set of vectors does form a basis for R3. Which means we also select the third set of vectors because they do form a basis for R3. I hope you found this helpful.